Hi everybody, welcome to another video in Pre-Calculus section 11.3 Geometric Sequence and Geometric Series. A sequence is a function have particular terms. A series is the sum of the sequence. Alright, we get there. But first, geometric sequence. Definition. Geometric sequence is defined as we have the first term is equal to a constant. We know the first term, and the next term divided by the previous term is equal to a constant, and that constant is called the common ratio. And we have the first term is equal to something, and then to get to the next term, from this term we multiply by that constant r, so r is a common ratio. Right, so we say determine whether the following sequence is a geometric sequence. So let's see, from this number to the next, what do? We have to multiply by some numbers. 3 times 4, 12 times 4, so that's correct, and then times 4, yeah, so that's, we have the same number, so this is a geometric sequence. It is geometric sequence, and the common ratio is equal to 4. That number we to obtain the next term, we take this term multiplied by that number. Right. How about this? So if we write out a few terms, let's say when n equal to 1, we have 3 to negative 2. It will be very misleading if I write like that. So let's just say a1 is 3 to negative 2, which is 1 over 3 square. a2 is 3 to negative 2 times 2, which is 1 over 3 to the 4th. Right, difficult to see, but if we have a of n is equal to 3 to the 2 to negative n, and if we use, and if we write like that, we won't be able to tell. But if we write this term is 3 to the negative 2n, and a of n minus 1 is 3 to the negative 2 n minus 1. Multiply this out, 3 to the negative 2n minus 2 minus 1 plus 2. And now ultimately we're going to divide them to see if we have a constant. So we take a of n divided by the previous term, a of n minus 1. So we take the ratio of consecutive terms in general. We have 3 to the negative 2n over 3 to the negative 2n plus 2. We divide two numbers with the same base. We will subtract the exponent. Subtract the exponents. Negative 2n plus 2n minus, that's a minus 2, and cancel out, we have 3 to the negative 2. Now we take the ratio of consecutive terms, and we have the constant, and that constant we know is constant because it doesn't depend on n. So yes, this is also a geometric sequence where common ratio is this, 3 to negative 2. So the ratio of consecutive terms are constant because there's no n in it. So yes, it is also a geometric sequence. Right. Now the formula for the geometric sequence, the n term of geometric sequence, is easy. If we start with the first term, right, to get to the next term, we multiply by r to get from this to the next. and we will multiply by r again to get from this term to the next. So we have an r already, then we multiply an r again, but one more time, so make it a square. And then one more time, and we just keep going. So notice that on the second term we have r to the first, the third term we have r to the second, the fourth term we have r cubed. So the power here is 1 less than the n itself. So that's why we have this formula. Right. Now let's look at this sequence. Find the formula for the n term, and after that find the ninth term. So it's simple enough. For this sequence, to get from this term to the next, what do we have to multiply by to get from this number to the next? Well, 3 multiplied by what is equal to 2. So we're just going to set up. We know that 3 multiplied by r is equal to 2. So with that we have r is equal to 2 over 3. And we know obviously the first term is 3. So we know the first term, we know the common ratio. That's all we need for the n term in the geometric sequence. a1 r to the n minus 1. Of course the common ratio cannot be 0, otherwise everything would be 0. Right. So a1, the first term 3, r to the n minus 1, 2/3 to the n minus 1. Right. So good enough. Yeah, we can just leave it like that. Now with that, if we want the ninth term, so meaning n equal to 9 and a9 equal to 3 2/3 9 minus 1, right, 2/3 to the 8, right, 3. This might not give us a fraction. 2 divided by 3 to the 8th power. Can we get fraction from this? Oh, good, we still can. So 256 over 2187. Right, simple enough. Just one formula, straightforward. And just like arithmetic sequence, we need the common difference and the first term. This one we need the common ratio and the first term. So basically arithmetic sequence or geometric sequence, we need to know what is the first term and how do we get from the first to the second, and from the second to the third, and so on. Alright, so that's all we have for the n term of a geometric sequence. Now if we want the sum of the first n term of geometric sequence, by the way, this formula is terribly wrong. This one is correct, but this one's wrong. So the sum of the first term all the way to the n term is given by this, or we can also say a1 r to the n minus 1 over r minus 1. Yeah. So either 1 minus r to the n, 1 minus r, or we flip the r to the n minus 1 and r minus 1. Right. Let's take a proof at that. So first we have the sum of the first n term, right? So we have a1 plus a2 plus a3 all the way to a sub n. Now, if it is a geometric sequence, it will be a1, a2 is going to be a1 times r, a3 is a1 times r squared, all the way to r sub n is a1 r to the n minus 1. Right, so that's what we have. Now, what we do next is if I multiply everything by r, so if I multiply r into s and just multiply r to everything, so then we just have a1 r, a1 r squared, a1 r cubed, and a1 r to the n. Right. Now, next, what we do is we throw the negative in front of that. Negates everything we have here. And we have negative a1r, negative a1r squared, negative a1r cubed. All of them are negative. Now, if we combine this with this, if we add side by side, if you will, we have s and minus rs on the left hand side, right, I'm going to write this first and I'm going to write that a1. By the way, right, if you take a look at that, if we combine them, a1r minus a1r, a1r squared minus a1r squared, and then so on. So pretty much it cancels everything. So when we do that, I'm just going to write a1 minus a1r, and then start from that term, a1r, and then minus a1r squared, right? Just one term on the top, one term at the bottom, one term at the top, one term at the bottom. Just keep going like that. a1r squared minus a1r cubed, and dot 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 a1r to the n minus 1 minus a1r to the n. So what we have is the first term is positive. By the way, when we write like this, one positive, one negative, one positive, one negative, one positive, and one negative, right? Notice the negative, we cancel the next positive. So we cancel this with this and that all the way to pretty much we cancel everything. When we cancel everything, on the left hand side I will factor out s and 1 minus r, and on the right hand side all we have is just the first term and the last term where I factor out a1, and we have 1 minus r to the n, and then we solve for s. We're going to have a1 1 minus r to the n, 1 minus r, and that's the formula we need to prove. Next, I usually prefer to write this one. Of course, you can write r to the n minus 1 and the r minus 1 at the bottom, which is fine, but I'll stick to that. Now, find the sum of the first 10 terms. So we know there's 10 terms for this sequence. We know the first term of the sequence. We don't know the common ratio, but it's easy to determine, right? So from this to the next, what do we have to multiply to get to the next number? Well, you see, it's negative 2, right? So what we have about this sequence is that we have 10 terms, right? We know the first term is negative 1, and the common ratio is negative 2. And the formula, the sum of the first n term is equal to a1 times 1 minus r to the n, 1 minus r. Now the sum of the first 10 terms, we're going to put 10 in for n. The first term we do know is negative 1. 1 minus the common ratio to the 10, and then 1 minus r is negative 2. So in that case we will have negative 1 minus negative 2 to the 10. Excuse me. Negative. Make sure you put that in the parentheses. Negative 2 to the 10. It's going to be positive. One minus negative 2, so that's 3. So we have that. So we have 1 minus that divided by 3 and throw in the negative sign. So that's going to be positive 314. Of course, we can just do this. Negative a fraction 1 minus negative 2 to the 10 power over 1. This is silly, but yeah, right. Of course, if we enter it correctly, right? Yeah, so that's what we have. Right, so that is the sum of a geometric sequence. Very straightforward. We have the formula for the n term of geometric sequence, and now the sum of the geometric sequence. Now, next what we have is the geometric series. By default, when we say geometric series, we refer that to an infinite geometric series, meaning that this will go on forever. Infinite dot 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 go on forever. Now, if that is the case, when the series goes, the term have to get smaller and smaller. If the term get bigger and bigger, when add up, it just the sum just get bigger and bigger. Essentially, if the sum exists, this has to go down. The term have to go smaller and smaller. Essentially, it goes to 0. If you add 0 at the end, that doesn't change. So that's the idea. So the sum of the geometric sequence, meaning the sum of the geometric series, if we add everything from the first all the way to infinity, then the sum is equal to the first term divided by 1 minus r, only if absolute value of r has to be less than 1, meaning only if r is between negative 1 and 1, and cannot be equal either. If r is between negative 1 and 1, then the sum exists and equal to that number. So let's look at the example here. We have 1/2 plus 1/4 plus 1/8 plus and so on. So in this sequence, what we have is the first term is 1/2, and the common ratio to get from this term to the next, what we need to multiply by is we multiply by 1/2, right? So once again, when we talk about this series, we mean it is a sum. So that's why we have the plus in the middle, right? We have the addition. Yeah, as opposed to a sequence, it's just individual terms and not a sum. All right. Now the ratio from 1/2 to 1/4, we need to multiply by 1/2, right? So pretty much half, the next number we just cut in half, the next number cut in half. And then the sum of the geometric series, we don't need to have any subscript here, is equal to a1 1 minus r. That is if r is between negative 1 and 1. And r equal to 1/2. So yes, we check that box. The first term is 1/2 over 1 minus the ratio is 1/2. 1 minus 1/2 is also 1/2. So we have 1/2 on the top and then 1/2 at the bottom. 1/2 divided by 1/2. Of course, the number divided by itself is 1. Or you multiply reciprocal, 1/2 times 2, also 1. But either way, it is 1. Now, did that make sense? Now think about this. Let's say if we have to travel that much distance, right? The whole distance. First, we have to travel half of the distance, right? And then we travel half of the remaining distance, which is 1/4. And then we travel half of the remaining distance, 1/8, and so on. Doesn't matter how close we are to the target. That distance always can cut in half. So we just cut in half, in half, in half, indefinitely. But if we add all of them up, essentially, we will travel the whole distance, right? So that's the idea. That's why the sum is equal to 1. That makes perfect sense here. Right. Now, let's look at this. Let's write down what is the first term. This one obvious. 3. The common ratio going to be this term divided by the previous one. So I just take this term divided by the previous one, and that is the common ratio. And before I find the infinite geometric series, must need to check if the common ratio is between -1 and 1. In that case, yes, it does. It is. So we can say the sum is equal to A1 over 1 minus R. The first term is 3. The common ratio is -2/3. So 3 over 1 minus a negative, that's a plus 2/3. So what I do is I will multiply top and bottom by 3. So I will have 9 on the top. 3 times 1 is 3. 3 and 3 cancel out is 2. So I have 9/5. Right, let's check. One big fraction, 2 divided by 1 minus -2/3. I just have to enter the number correctly in the calculator. Sorry. Right. Nine, 3. Yeah. What did I enter there? Is that? Yeah, I think I actually hit the second, so that is a Z, not a 2. All right. So yeah. Right. Next, we find the sum of this geometric series. Same thing. The first term is obviously is 1, and the ratio to get from this to the next, we take the next term divided by the previous one. So we'll take 5 over 4 divided by 1. It's going to be 5 over 4. Before we go any further to find the sum of the geometric series, we check to see if R is between -1 and 1. And in this case, 5 over 4 is 1.25, which is known. So the sum does not exist. Right. Next, we can write this decimal number, repeating decimal number as a fraction. If we write 0.3 as 0.333 indefinitely, so that means we can write 0.3 plus 0.03, 0.003, and so on. So for that series, the first term is equal to 0.3. The common ratio is this divided by the previous one. That should be 0.1. And we will check between -1 and 1. 0.1 is between -1 and 1. So yes, that check. So we can use the sum, which means this series is equal to A1 1 minus R. The first term is 0.3. common ratio is 0.1, so we have 0.3 over 0.9, and that cancel out is 1/3. Because if we use the calculator like this, 0.3, I'm sorry, 0.3333333, convert to fraction, it does that too, but of course don't try that. It works, but anyway, it's much better to do this. Alright, convert the repeated decimal to a reduced fraction. So we have 1.27. Repeating decimal, it's going to be 1 plus 0.27, which is 1 plus 0.27, and then we can skip 0.0027 and then 0.123427 and then so on. Notice that the 1 is different than any of this, so we're going to keep the 1 separate. Now if we look at this, this will be a geometric series with the first term is equal to 0.27, and the common ratio, we're going to take the next term divided by this term, and do that, we have 0.01, and because that ratio is between -1 and 1, so we continue this, we have 1 plus the whole series will be given by a1 1 minus r. So we're going to have 1 plus a1 0.27, and then 1 minus the common ratio 0.01. So we have 1 plus 0.27 over 0.99. Now if we move the decimal places to the right, 2 places to the right, we have 27 over 99. So we can just use fraction there. And we can convert that to fraction. It's 14 over 11. Of course here we can reduce top and bottom by 9. That gives us 3 over 11. Right, so simple enough. So the geometric series, the sum is that, but the ratio has to be between -1 and 1. Now let's look at one application. Initially, pendulum swing through an arc of 15 inches, like that. On each successive swing, the length of an arc is 0.98 of the previous one. What is the length of the arc of the 10th swing? Alright, so original is 15 and each one of them is 0.98 afterward. So we can write like this. The first term is 15, say, inches, and the next one is equal to the previous one times 0.98. We can write in the recursion relation like that, and of course when we write like that we can say the ratio by that most is 0.98. Right, and we want the length of the 10th swing. So the formula h of n is equal to a1 times r to the n minus 1. Now we want 10 terms. The 10th term, a1 is 15, and we have 0.98 is the common ratio, 10 minus 1. So we have 15 times 0.98 to the 9th power. We have 12.5. That's just one decimal places. Okay, 12.5. The units will be inches. Right, now after 10 swings, find the total distance with the pendulum have swung. So this is the formula for the n term. This one we want the total distance, meaning that we want the sum of the n term, which is a1 1 minus r to the n 1 minus r. Now we have the sum of the first 10 terms. The first term is 15, we know that. 1 minus 0.98, which is r to the 10 power over 1 minus 0.98. Right, so we have 15 times a fraction. On the top we have 1 minus 0.98 to the 10 power. At the bottom 1 minus 0.98, and we have 137.2. just keep one decimal place, 2 inches. When it stop, what is the total distance? So we assume this one just go swing indefinitely. Of course, doesn't matter how small the number is, we can always multiply by 0.98. It's just like the concept with the distance we travel. But if it is extremely small, then even though it's technically still moving, but we don't see the difference. So in that case, because even when the distance is too small, we won't be able to see it. But it doesn't matter how small the distance that travel is, we can always be able to multiply that by 0.98. That concept is the sum of the geometric sequence. I'm sorry, this is the sum of the sum of geometric series, meaning that it go on forever. And in this case, the ratio is between 0.98 and it is between -1 and 1. Yes, so the sum of the geometric series or infinite geometric sequence, the sum of infinite geometric sequence, the A1 is 15, have 1 minus 0.98. 15 divided by 1 minus 0.98, and we have 750 inches. Right, so that's pretty much all three formula we have in this section. But that formula only between -1 and 1, because if r getting bigger than 1, the next term is going to get bigger and bigger, and the sum in that case just get bigger and bigger, and it does not approach to any number. Right, we have one more business application. Annuity. An annuity is a sequence of equal periodic deposit that may make in some periodic annually, quarterly, monthly, and so on. When deposits are made at the same time that interest is credited, annuity is called ordinary. When we deal with that, we have the ordinary annuity here. So it can be shown that the amount at the end is going to be equal to the payment times 1 plus the interest to the n minus 1 over I, where I is the interest for each period, each payment period, and P is the payment. Let me attempt to write this out. So let's say we make retirement plan, for example. the first year we make a deposit of $1,000. Let's say each year we make a deposit of $1,000, but the interest, let's say for simple, 10%. So that $1,000 to make in the first year, in the next year, that with 10% interest, you have $1,100. In the next year, with 10% interest, we have this much. And then next one, I think is 1331 probably, and then keep on. Right, so that's what we have. But at the same time, on the second year, we make one more 1,000, right? And then the next year after that, generate 10%. And then we have this. And at the same time, in the third year, we make 1,000. And that, in turn, generate interest as well. So what we interested in, what we want to know is how much to say, let's say after 4 years, how much we have. So that pretty much we have 1,000 times 1,000 times 10%, 1,000 times 10% times 10%, plus 1,000 times 10% to the third. So let me write this. 1,000 is 1,000. That one is 1,000 times 1.1, because it earned 10%, which the original 100%, so that is 1.1. And then that one is going to be 1,000, 1.1 to the second. As you see, if this one keep going, this is the sum of the geometric sequence, and that formula is this. So technically we should have the common ratio. The first term is P. The common ratio is 1 plus I, right? Let's say it's 10% interest, meaning that it's going to be 110% for the next one. And then we write the sum, the total money, going to be the first term. In this case, I will write R to the n minus 1 over R minus 1. Because that's the sum. We can use either this one or that one. I'll use this one here. And R to the n, because A1, the first, is the payment. And then 1 plus R is going to be R. I should write 1 plus I for R minus 1. And at the bottom I have 1 plus I minus 1, R minus 1. Of course 1 and 1 cancel out. That's why we have this formula, right? So this formula is just a sum of geometric sequence. Right, now we have an example. To save some retirement, for retirement, place 5,000. So we have 5,000 as the end of each year for the next 40 years. So we have a few things here. The payment P is 5,000. N for 40 years. And what will be the values of the individual retirement account? Assume that it is 7% a year, and we pay for each year, so that's 70% a year. So the interest rate 7%. Right, and we just use, of course we can write using this formula or that formula, or just what we are given. Let's wait 5,000. One plus I, 1 plus 0.07 to the 40 minus 1 over 0.07. 5,000 times a fraction on the top is 1 plus 0.07 to the 40 power minus 1 over 0.07, and we end up with that much. 998,175.56 cents, right? So almost a million, right? Yeah, even though we only pay $5,000 for 40 years, so the total we actually pay is only $200,000, but the interest generate a lot. So that's why they usually encourage us to save money early and often, because the interest is pay off in the long run. Right. By the way, this is also a lot because 7%. Yeah, but that assumes that it is 7%, the same thing for every year. But sometimes it could be more than that. Sometimes it could be lower than that. Sometimes the 7% is not going to be there for it's not going to be constant for the long run. But if assume that it is 7% throughout for 40 years, that I think is the big high interest rate, which is very, very good for investment. Right, so that's all we have in this section. Geometric sequence, the formula for the n term, the sum of the first n terms. The sum of geometric series is that, but only when r is between -1 and 1. And then we have some application. That's all I want to cover in this section. As always, thank you for watching, and see you in another video in Precalculus.